Section 13.7 is surface integrals. So we'll extend on what we did in 13.6 to integrate a function f or some scalar function of variables x, y, and z along a surface S or over a surface S. We'll describe a physical interpretation of this later on in the notes. But to get started, again, we're looking at a vector function parameterized by u and v. So u and v are some plane or some region in the plane, D, right? That's again called the parameter set or parameter space. And R is some warping of this UV, this planar region D into some three-dimensional surface in R3. So and that's given by these three components here, just as we had in 13.6. So to make things easier, we'll assume that D is a rectangle. Of course, all this can be done if D is probably a type 1 and type 2 region or something like that. But just to keep our derivation straightforward and not to get into too many of the details here, we'll just assume D is a rectangle. And then, of course, we divide D into subrectangles, R sub ij with dimensions delta ui and delta vj. And then our surface subsequently is divided into patches, S sub ij. And this is just as in section 13.6. Now the only difference is we're going to evaluate f at some point pij. That'll be within our region rij with those dimensions. Take it to be the bottom left corner or some central point in that little subrectangle. Either anything is fine, because as we shrink those, the point pij will be stuck inside its own rectangle no matter what. And multiplied by the area of the patch, which we'll denote as delta Sij, we can form the Riemann sum given here. So we're approximating the evaluation of the function f over the region D along the surface S. Okay, so everything is parameterized underneath in terms of u and v. And what we're essentially doing, this is kind of similar to a line integral, where this would have been some section of the curve that we're evaluating our function over. Now it's some section of the surface that we're evaluating our function over. And if we add up all of these function values times these surface values, then in this double sum, to go in the directions along u and the directions along v, or vice versa, then we'll get an approximation of the function's value over this surface or along this surface. So it's very similar to a line integral, only now the line or the curve is actually a surface. So it's got two parameters in it instead of one. So this, of course, as we take the limit as the max delta u and delta v goes to 0. In other words, we're shrinking our subrectangles and consequently our patches on our surface S. We can define our double integral of the function f on the surface S via this Riemann sum, the limit of this Riemann sum. So that's more or less follows the sketch that we used in the last section 13.6 to establish the surface area of a given surface S. Now the only difference is this function f takes on values other than 1. So that would be the big thing to note, is that we could, if f is a function that's just identically equal to 1, in other words, it's 1 for all values x, y, and z, then all we'll be computing, in fact, is the area of this surface. So we'll see that in some subsequent results later on. Now, remember that each of these patches, delta Sij, we want to dig into that a little bit further, because as is, this version of the integral here doesn't really tell us much. Evaluate the function f over the surface. We don't want to do it by a Riemann sum and a limit. We want an integral formula. So to that end, we go back and look at what these delta Sij's are. Well, remember that that is the area of a patch. And in the previous section, we were able to approximate that area as Ru delta U cross Rv delta V for each ij, for each subpatch. Okay, so, and we've just factored these two constants, the delta U and delta V, outside of the magnitude of the cross product because they are in fact scalars and they're positive, so they'll pass out of the magnitude bars nicely as is. So with this in hand, when we take the limit as these subpatches go to infinity, the number of them, and as their dimensions go to 0, delta U and delta V become du and dV, and du dV is really just dA. But really the thing to note in all of this, the link between differentials is this. ds is actually equal to r, so, and remember this is the partial with respect to u, partial with respect to v, cross together magnitude dA. So we see that this piece here is swapped out for this piece. And the reason we do that is because, well, we need to be able to actually calculate this. ds is a handy notation, but it doesn't tell us how to actually calculate these things. And of course, we're going to plug into f, or f's argument, the vector function r of uv, so that way we actually travel along this surface S that r describes. So let's compare this to a line integral. I know I started to do that before. We see down here that similarly, this is little s, and little s just represents the arc length for a curve C parametrized by R. And our definition for a line integral for a curve C that was parametrized by R was given by this. Note that there's just one parameter, right? R, of course, is a vector function. It's just parametrized by the parameter t. So it's a filamental, it's a curve, a line, something that's not a surface. It's not a two-dimensional object. It's just this line in three-dimensional space, or this curve in three-dimensional space. So this formula is quite a bit more simple because we really only have one derivative for such a curve with respect to t. And we could come up with that. Now, contrast that to above, we have two parameters. So we had two different derivatives we might consider with respect to u and with respect to v. And it just turned out in our formula, thanks to that area of a parallelogram for those subrectangles or patches, that this cross product and the norm is what we use, or magnitude is what we use. Also notice the magnitude of this vector is involved as well. So this is really just a two-dimensional version of the line integral, as I was saying before on the previous page. Now that we see it right in front of us, we have a nice analog. So also, another thing that's essentially corollary to this formula, and just follows from it directly, is that if f of x, y, z is just identically equal to the function 1, in other words, it's 1 along all of this surface S, well, then we get our area formula that we were using in the previous section. So remember, ds is equal to this portion of the integrand and the differential. And we've got exactly the area formula we had before. So this formula above reduces to our area formula as a special case. Okay, they ask us first to compute the surface integral of the double integral over S, x squared ds, where S, our surface, is the upper hemisphere of the unit sphere centered at the origin, just to make that short. So we'll need a parameterization first, and we're essentially switching to spherical coordinates to do this, but we're just really doing that with more of the mindset of parametrizing the sphere in terms of phi and theta and our function r here. We did that in the previous section. Note that that had an a or a 2 or whatever the radius might be. In our case, there's a 1 here for all of these components, since the radius is 1. That's understood, so we don't need to plug that in or write it. So we also make a note that our x value is this. So x squared, which is actually in our integrand, it'll be useful to have this around once we identified what our parameterization is. X squared will be this. This will be the function we input into our double integral once we get going with the double integral. But we know that, from above, we need to establish some things. We need to find RU cross RV and the magnitude of that vector. This calculation, or one like it's been done in the previous section's notes. It's also done in the book for a general sphere of radius A. So you might use a shortcut instead of actually going through all the work we do here. But we'll first need R sub phi, the partial derivative with respect to phi. That's given as follows. Do the same for R sub theta. It's given here. Now we take R phi cross R theta, and note that, our parameterizations in the future might have been R theta phi, we might have switched the order of these things, and we could flip this cross product, and that would usually change the sign, but what we're ultimately interested in is the magnitude of that cross product, so the order of this really wouldn't matter. We do want to be careful, though, that we take the correct order for what our intentions are. So anyway, in this case, that's not anything to worry about. So there's our determinant of our two vectors r phi and r theta for the cross product. It's this matrix determinant. When we simplify all that, there are some steps missing. Of course, the viewer can verify those steps. We end up with this vector as our cross product. The next step is to find the magnitude of that vector. This is done below, right here. This is the square root of all three of the components squared and added up. Note that here, this component squared plus this component squared has a cosine squared theta and a sine squared theta with a sine to the fourth phi and a sine to the fourth phi. So really, cosine squared theta plus sine squared theta adds to 1, and that just leaves us with 1 multiple of sine to the fourth phi, and that's exactly where this term comes from. The other one's pretty obvious. You just square the z component, and it just sits as a sum in there. Factor out sine squared of phi to have a sine phi outside the radical. Then we end up with sine squared phi plus cosine squared phi. That's 1. So overall, our magnitude, luckily, is just sine phi. So this is the component, or the multiple that goes into our integral. So this will fill in for this portion right here. It's just sine of phi, and then f of r of uv, well, that's going to be given by, we know that x squared is f, and that's just going to be sine squared phi cosine squared theta. So putting all of that together, we have this, our integral x squared over ds. Now we're going from 2 pi, 0 to 2 pi and theta, so all the way around the xy axis to get the full circle that is the base of the hemisphere. And then we'll note that we only want to go from 0 to pi over 2 in phi, because remember, phi is the angle made with the x-axis, or sorry, the positive z-axis. So if that's the case, this is z, down below is the xy plane. We only want to travel here for our angle phi. And then, of course, all the way around for our angles theta, and that'll give us the hemisphere on top of the xy plane. So anyway, that integral is now set up. We've got sine squared phi cosine squared theta times sine phi. So this was our f of r of d theta, and this is our r phi cross r theta magnitude, d phi d theta. And this is just some standard trigonometric integrals. Note that these two functions are just multiples of each other. Anything with respect to theta and phi are just multiples. So I've split those integrals up as multiples against each other. And we've got this and this. This is a conversion of sine squared phi. And that choice has been made to use a u substitution and resolve that integral. And, well, cosine squared theta has this as its antiderivative. This is the antiderivative of the other integral. Apply the limits of integration, and we'll have 2 pi over 3 in the end. Fairly simple answer for a fairly complicated approach. So that is our first problem, and that's dealing with a parameterization for a surface given in terms of r and 2 parameters. In this case, they were phi and theta. They could have just as well have been u and v, and using this initial formula that we have up here, much like the line integrals we've dealt with in the past. Okay, now of course we'll have a graph version of this when we're talking about a surface z equals g of x, y, and that's just another way of taking on one of these surface integrals. We'll see that here now. So z is equal to g of x, y. When we have such a surface, then we can quickly parameterize that as x equals x, y equals y, and then z is equal to that third parameter. Remember, this is sort of that default parameterization. It's the easy parameterization to come up with. Now, if things work out, and this is an easy way to write to form our integral, this is a great way to go. We've got a formula here that's been built. I think we've seen this in the past already. If the reader's unsure about it, then of course it's suggested to actually confirm that this is equal to that determinant I, j, k, and work out the details of partial with respect to x, y, and z here. And this is x, y, and g of xy. Right? And I think that we'll see if we work out the details of this, we get exactly the formula that we're given here. So that's just the cross product. Then the magnitude, so I'll add some bars to this. The outer bars are the magnitude of that vector. We should end up with exactly what we have in that radical. So of course, this could be changed if y was equal to some function of h of x and z, and then z was just z, then of course things would swap out in a very natural way. And in fact, just using, as long as we're not spatially arranged in a certain way, we wouldn't have to worry about how we move things around in here, but just a quick renaming convention would let us be able to, in other words, just redefine it so that z is again this function. You know, do it like this, say y is z prime now, right? Or if you don't like z prime, z star, and z is y star, switch them out, and then we'll have the exact same formula for our cross product. At any rate, the textbook has some details for that, and if you're not sure, of course, you can always just carry out this calculation just to have it. You just don't want to have to do that every time. So most of our surfaces are given as z equals g of x, y in problems like this, so you don't have to do that too many times or really worry about that too much. Our integral formula in this case, this is just using the fact that, remember, this is the function x, y, z, ds is the function evaluated at x, y, and z. Now, it's no longer r of u, v. Our parameterization is given by x is x, y is y, and z is g of x, y. So our parameters are x and y, and z is based on x and y. So everything is in terms of two parameters. That's the key thing here. And times our cross product for the tangential vectors for our two parameters x and y, well, is given as in the formula above. So that's our new dA or ds substitute here. These two things are the same in this case. Okay, so with those quick derivations in hand, we've got a really nice formula we can apply to a surface defined in this manner. So we're asked to evaluate the integral of y over the surface ds, and the surface S is given by z equals x plus y squared. It's not a typo, it's just x plus y squared. On the rectangle, x between 0 and 1 and y between 0 and 2. So we start, declare the thing we want to compute, and we can quickly write our integral down for what it's worth. If we needed to repackage that, if that was a circular region or something, we might repackage it into S and convert to polar coordinates. In this case, representing a rectangle, a true rectangle, a Cartesian rectangle with corners. It would not be wise to convert to polar coordinates. It's hard to do that in polar coordinates, so we just kind of cross our fingers here and hope that this will work out in the end. Well, we use the formula given here to come up with our ds component, right? dA is equal to, or ds is equal to this derivative, or this term, dA, and in this case, dA is dy dx, okay? So we need our derivative of z with respect to x, that's 1. These are partial derivatives. Partial derivative of z with respect to y is 2y, coming from that term. And we have 1 plus partial z with respect to x squared plus partial z with respect to y squared. We get these two terms. This gives us 2 plus 4y squared underneath the radical. We can factor out a root 2 in here, or, sorry, we don't do that. Sorry, we just let this be a u substitution of the full term. We could factor out root 2 if we wanted to make a different u substitution, but this is completely sufficient. So if that's u, du is 8y dy, so taking the derivative of this term with respect to u. We have a substitution now for du, which is, or for dy, which is 1/8 du based on, so y dy is 1/8 du. And that's how this swaps out here, 1/8 du. And square root of u is given by this term. And our limits of integration, u at 0 is 2, u at 2 is 18. So we've changed that from 0 to 2 to be 2 to 18. From here, this is a straightforward integral. We've converted everything, including our limits of integration. So we arrive at a single integral that looks more or less like this. Applying our limits of integration, we get a term that looks like this. This is the integral from 0 to 1 of dx. So it's just x from 0 to 1, which is 1 minus 0. And simplifying all of this, we arrive at our final answer, 13 root 2 over 3. So we're being a little bit faster with our double integrals now just because we're doing lots of the same things over and over. Hopefully that's the case for the work that you're doing in these sections as well. So oriented surfaces, we have a definition to get to before we can really talk about the vector form of these surface integrals. Of course, we want to get to a vector form for surface integrals, much like we had or have a vector form for our line integrals. We'd like to do the same on our surfaces. Now, remember, when we talked about line integrals on closed curves, we had an orientation. We traveled a curve in a counterclockwise method. We define that as our orientation. Right? That looks bad. As our orientation, something like this. We're moving counterclockwise. We're keeping the region on our left as we travel through here. Well, it's a little bit more difficult to speak of orientation, and particularly to draw it for a surface. But we'll note that there are surfaces that we can come up with in three-dimensional space that are not one-sided. Okay, so a Mobius strip is what I would suggest as the prime example. The textbook talks about how to build one of these. A non-oriented surface, an example of one, is the Mobius strip. There's an umlaut there. Don't quite remember the Mobius strip. Basically, it's a rectangular strip of paper with one twist in it, and then tape the two ends together. And you'll see that if you put your pencil on one side of that and draw a line down the center of that little strip, that you'll eventually come to the point where you began your line, and you'll have drawn a line on what seems to be all sides of the surface. And what that will convince you of is you have a surface that only has one side. So we cannot consider such a surface because our normal vectors wouldn't be defined there. So we'd have a normal vector that points one direction off the surface, and then as we lapped over it on the same side, essentially, it would point in the opposite direction, and that would be problematic. So most of what we'll deal with will be oriented surfaces. In fact, everything we deal with will be oriented surfaces in this section. So if you're not too worried about what all those things are, you can kind of leave that off to its own. So we'll talk about a surface S that's oriented, and it'll have a boundary of S right here, and all kinds of nice things about that surface. It'll be called orientable if it has or oriented if it has a unit normal vector everywhere that is non-zero and varies continuously over S. Okay, so this is all the exposition that we see below. So if we have a continuous normal vector over S, then we know that S is oriented. Again, we're not going to see surfaces that are not oriented for the sake that we can't actually compute these easily without an oriented surface. So what we'll do is we'll typically talk about we need to pick an orientation for one of these oriented surfaces, and this normal vector n provides us with a good choice for doing so. Okay, we'll choose the outward pointing normal in all these cases. Okay, so the normal that points, if the surface encloses some solid, like a sphere, it would be the normal vector that points outward from that solid or away from the solid. So just note that if we were talking about a sphere, this is what some of the exposition below is going on about. If we were talking about a sphere, we'd have two choices, right? If we're looking at maybe this profile view where this normal vector is pointing orthogonally away from the sphere, it's a tangent vector or some tangent plane that it's orthogonal to, then we have two choices. We could point out from the sphere, out from this solid that's contained by this boundary of S scenario, right? Or we could point, or boundary of the solid, or we could point, and that in fact is just the line. Remember that S itself is the full region here. So that full surface given by this. Or we could point inward, right? So one of these is in, and the other one is negative in, is the way we'll take our definitions. So one vector points away, the other vector points inward. So if we have a surface, an oriented surface that's given by the graph of z equals g of x, y, the natural orientation of S is just the unit normal vector, and that's going to turn out to be an outward pointing vector. Remember that the unit normal vector is calculated by this. How do we get that? Well, the top portion of this, remember, is G sub X cross, it's actually the vector 1, 0, G sub X crossed with 0, 1, G sub Y. The details of this are in the book. We can carry out that there or on your own. This is the magnitude of the cross product of the above. So it's the magnitude of all that. Or as you see it in the formula, it's this is the magnitude of all of this. K gives you the 1, partial z with respect to x squared, partial z with respect to y squared. That's this term and this term respectively. So it's all there. We hope to not have to use that normal in these future situations when we talk about the vector form of this, and that will be the case. We'll see a cancellation a little later. That'll be kind of nice involving all of this. So just kind of leave some details open there for us. Yeah, actually, there's our normal definition here as well, right? And remember that in this case, R is in fact the vector, X is U, we could say Y is V, and then this would be G of U, V. So we carry out the details, that we see above up there with this, then we'll get exactly this formula right here. Okay, so that's a bunch of hasty semi-derivations. The book's got the full details, and I think I've pointed us more or less in the right direction. So opposite in, of course, is always this negative in. We'll only take that if we're told to use a different orientation in problems that we might consider. So real quick, let's calculate the normal vector of a sphere of radius A. Okay, so let's find this normal vector. First things first, we need to calculate the cross product of r phi and r theta, the partial with respect to phi, then the partial with respect to theta. We've done that before, only now the difference is with a parameter a. Remember that there's some work that's not being done in front of us. The magnitude of all this, thanks to some trig identities, works out to be this, a squared sine phi. And with these two things, we use this formula above to find the normal vector. It's this vector we're given, we found, cross product, divided by its magnitude. When we simplify all of these things, what we arrive at is a vector that looks like this. And we should note that that vector is actually the normal vector to a sphere of radius 1, right? This is the parameterization, actually, of a sphere of radius 1, and that's exactly what we would expect to be the case if we're finding the unit normal vectors to a sphere centered at the origin with radius a, right? No matter how large that sphere is, any point on that sphere, as we see above here, any point on that sphere should have a unit normal vector that points away, in fact, in the same direction as the point that got us to that sphere. So these things should be very similar. Maybe they should have been in red to not be confusing for the fact that it's pointing outward like the other one. So that's an interesting thing to note, kind of a cool problem to see that to see the intuition behind it or the geometric aspect to it. So we hope to not compute that normal every time, and that will be the case. So let's look at how to do so and how to interpret these surface integrals of vector fields. Okay, so if we let S be an oriented surface with a unit normal vector n, then we'll imagine some kind of fluid. Either the fluid is some sort of ethereal thing that passes through the membrane, or the membrane is some kind of very permeable net-like surface or imagined situation. Or even, moreover, we could think of the flow as being sort of a magnetic flow, right? Or flux, even, is the term that we're going to see towards the bottom. So again, going back to a fluid representation, rho of x, y, z will be the density of the fluid given a point in space, x, y, z. The velocity at that point in space is v. It's flowing through this surface, the face of this surface, which is imagined to be somehow permeable. Okay, so here's S, our surface in three-dimensional space. It's been drawn with a little bit of curvature to it. And then we're looking at some subregion or some patch of S, Sij, this little blue patch right here. And it has a normal vector n pointing outward from it. And then we talk about rho v, the flow per unit area of this fluid. So again, if we think about what rho density in x, y, z is, it's times v. We're going to lose a length component, so it's per squared area instead of per volume. So it is the flow rate per unit area. And we realize that rho v dotted with n is the component of the vector rho v in the normal direction. So what we want to measure is the amount of this flow that's pushing through in the normal direction of S. So that's what we're going to measure on this for this surface integral. And as such, we know that the area of this patch, well, we'll just call it A of Sij. We know, of course, that will be a cross product later on, or some kind of normal vector definition. So here we have exactly this, as we see here, and that is the approximate amount of fluid that's passing through this patch Sij, or some sort of ethereal fluid or flux that's moving through this surface region in three-dimensional space. And of course, these are all evaluated at each point on Sij, or some point on Sij, as an approximation. Since those are all approximations in this highlighted portion, we would take a double sum across the i's and j's to get all of our two-dimensional little cells or patches that make up this full surface S, and we approximate the full fluid flow across this surface by such a sum. If we shrink all of those patches to infinity, or if we bring the number of all those patches to infinity by shrinking their dimensions, then we'll obtain this double integral that we see here. That's our definition via the limit of the double sum. And now we have the integral over the surface S of rho v dot n. And that's going to be, well, rho is a function of x, y, z, v is a function of x, y, z, and so is the normal vector. So we can write that out a little bit better, dot n x, y, z. So ds, we recall, luckily for us in terms of simplifying things, remember that ds is actually ru cross rv dA. And we'll get to that in just a moment. Things will simplify nicely for us. So now that we've considered this fluid flow situation, we'll in general think about F as being some kind of force or a vector field. In fact, if rho v is the flow per unit area, then we can think about force per unit area in a very similar way. And thus we'll swap out rho v with this vector field F. That's dotted with n now, with the differential ds. This is called a flux integral or a surface integral. It's very common in physics for vector fields, force fields like magnetic field, electric field, gravitational field, anything with field in its name probably. So as our definition then, if we have a continuous vector field on an oriented surface S with unit normal vector n, then the surface integral or the flux integral of F over S is given by our extreme, most concise vector notation is F dot ds. That ds packs a lot of information into it. It is F dotted with the normal to the surface S, ds, and we remember that one step further, in terms of actually trying to compute this, we need to recall that ds is actually this cross product's magnitude dA for RU and RV if S is parameterized by R of UV. And that brings this overall formula to be this more computable expression here. So F dot, the cross product, it's nice to see, we had an n here, normal vector, which would be hard to calculate. Only when n is multiplied by ds, this term cancels with that term in the denominator. So we just have RU cross RV dA. So the term that survives is this RU cross RV right here, and then the dA. So it turns out that it simplifies our vector form of this surface integral. Okay, so this is a much nicer thing to do than to calculate the full normal vector. Going a little further, if we're dealing with a function whose graph is given by z equals g of x, y, everything is got continuous first partials, g has continuous first partials, then f dot ds, which is equal to this, we can use what we found for graphs a couple pages ago in these same notes to write down what ds actually is, or what this cross product actually is. And we'll get that it's F, which has components P, Q, and R, dotted with the negative G sub X, G sub Y, negative G sub Y, one vector that is RU cross RV, or RX cross RY, or GX cross GY, however it is we want to think about it. Okay, dA. So this is a key formula when this is given in terms of a graph. Z equals G of X, Y, and not as a parametric surface, R of UV. But we've got either one in case we need it. So our last example, we're asked to find the flux of the vector field across the surface S with positive orientation, where our vector field is given by X, Y, I, and so on. Okay, and S is part of the part of the paraboloid Z equals 4 minus X squared minus Y squared that lies above this square. X goes from 0 to 1, Y goes from 0 to 1 with upward orientation. Okay, so everything's got a positive orientation. No need to introduce a minus sign for n or anywhere else. So positive and upward orientations are all checked off. And our flux integral is this in vector form. Of course, we expand that a little further. We get to this point. Still, we want to go a little further because we're dealing with g of xy equals z, or z equals g of xy. So we can use that last formula on the previous page, which is this one. And that's z's partial with respect to x, and it's partial with respect to y. P, Q, and R are these functions, P, Q, and R by component above. And from here, we just need to fill these in. We know that z with respect to x, partial with respect to x, is negative 2x. With respect to y, is negative 2y. Multiply that by each of these components respectively. And we end up with this expression in our integrand. We pause here and say, wait, we've got a double integral with 3 variables. Don't forget that z is given as a function of x and y. So we substitute for z, that function xy. And we see here, there's our function g of xy. There's 2y squared plus x times that function, times that z. So we essentially factored z away from 2y squared plus x. Everything now is in terms of x and y. It's a bit of a polynomial mess, but here we see we've organized everything by powers of y. Decided to integrate with respect to y first. Of course, those are interchangeable because we are integrating over a rectangle. Everything's constant, so it's not going to hurt anything to change the order. And being careful in doing so, we arrive at 713 over 180, as our answer. Of course, that's a pretty straightforward rectangular double integral. The only hard part is the details and keeping all the fractions straight. So there it is. Of course, there are other examples we could do where we would be looking at a surface that's parameterized by r of u and v, and then f dot ds would be given by not the graph formula that we have down here, but this formula right here. And that would follow just as well as it did in this example. So just note that there are different versions of this based on whether or not we're given a parametric surface or a graph in terms of Cartesian coordinates x, y, and z. So that's it for section 13.7. Much of it is just calculation and recognizing which integral formula to use, but it should be reinforcing our ability with double integrals and with vector calculus in general. So in the next section, we'll move on to basically the analog of Green's theorem for surface integrals now. So that'll be section 13.8. That's the divergence theorem, or Stokes theorem. Sorry, that's Stokes theorem.